In this video, we're going to talk about the production process and the costs of production. So let's start. Our main goal is to think about what cost curves look like and how a manager can manage their costs of production. The reason that a firm generates costs of production is that they're producing output. So in order to understand how costs behave, we need to go back a step and understand how production behaves. So we need to think about inputs, what we would call the factors of production. We need to think about how much output a firm can produce depending upon the amount of inputs it uses. And then once we understand that, then we can start to think about how much the cost of those inputs changes as the firm changes output. So we're going to be thinking about what we're going to call a production function. The production function just shows the relationship between the inputs that the firm uses and the output that the firm can produce. We're going to think about a couple of different inputs. We can think about capital, which would be the word that we use to describe buildings and machinery, but it can also be intellectual capital, so it doesn't have to be physical capital, but a lot of times that's what pops into your mind first when you think about capital. And we're going to use the symbol K to indicate capital. And then we're going to also be thinking about an input that would be labor, and we'll use L to indicate that. We could think about other inputs, so we could think about land. If this was an ag class and we were thinking about agricultural production, we could add land as another input. But for what we're going to do, we're going to keep it simple with just capital and labor. And we're going to think about a production function. Q would be the amount of output that the firm produces. And I'm going to describe this production function first just in general terms. So I'm going to say that output is some function of capital and labor. So that's the most general way to write it. F with the parentheses just stands for some function. And that function that we would use is going to have capital in it and it's going to have labor in it. Now I can specify that function. Let me give you just some examples. An example of a production function could be this. The amount of output is equal to 10 times K plus 5 times L. So that is a specific function. So we have replaced our general function with a linear function of capital and labor. And this says, obviously, that if you increase capital, output goes up, and if you increase labor, output goes up. In fact, if you increase capital by 1 unit, you get 10 more units of output if we ignore labor. So every 1 unit increase in capital, we get 10 units of output. And for every 1 unit increase in labor, we get 5 units of output out of that. So that's a particular example of a production function. We could also use one that's what we call a Cobb-Douglas production function. And that would look something like this, where we have capital and we could raise it to the 1/2 power multiplied by labor raised to the 1/2 power. So that exponent there, if it was a 2, if let's say instead of 1/2 this was 2, that would be K squared, K times K. But this is raised to the 1/2 power. Another way that you could write this would be the square root of K times the square root of labor. So that's another way. These are equivalent. Actually, you could also write it this way, just the square root of capital times labor. All three of these are the exact same thing. And that's a very commonly used production function. It has some nice properties, and we'll come back and use that here in just a little bit. Here's how you would use that, or either of any production function. Once you know the functional form of it, you would simply plug in the amount of capital and the amount of labor that you've got, And that would tell you how much output you can produce. So if we had 2 units of capital and 10 units of labor, we'd plug a 2 in there, and whatever I said, 10 units of labor, we'd plug a 10 in there, and out of that would tell us the amount of output that we can produce. Now, let's talk about the difference between the short run, I'm going to abbreviate the short run SR, and the long run. That's something in an economics class, especially where we're talking about production, where we would be thinking about the difference between the short run and the long run. And it's tempting to think that the short run would be some set amount of time that's not very long, maybe 6 months or a year, and then the long run would be anything past that, right? And in a lot of cases, that might be okay. But in an economics class, we don't think of the short run as a set amount of time. The short run is whatever period of time during which you have some fixed input. So in the short run, some inputs are fixed. That's how we define the short run. So for example, if you've signed a lease, and that lease runs for another 8 months, then at least in terms of your housing decision, the short run is 8 months for you. You're stuck with that lease for 8 months. There's nothing you can do about it. Now, if we go out past that, well, after that lease expires, then you can make a new decision about what your living conditions are going to be. But for right now, you're stuck. Okay, so in that case, the short run would be 8 months long. Or if your lease expired at the end of the month, let's say there's 30 days until the lease expires, the short run would be 30 days. So it's not a set amount of time. Okay? Now, what we're going to see is that these fixed inputs generate what we're going to end up calling fixed costs. Okay? So for that housing decision, that whatever your monthly rent is, that's a fixed cost for you. Let's say your monthly rent is $1,000. Then for the next 8 months, I can tell you what your cost of housing is going to be. It's a fixed cost, and it's $1,000 a month. After that lease expires, you can make it more, or you can make it less. But for 8 months, it's fixed. Typically, what we're going to be thinking about in a production process is that capital is fixed. So the building that you're working with, whether it's a kitchen that you're cooking in, if you run a restaurant, or whether it's a plant that you're making output in, or whether or not it's just a machinery that you're using to do whatever production process, we think of capital as being fixed in the short run. It's the period of time during which you're stuck with the equipment and the building that you've got. And the way that we would describe that with this production function notation is we would say, okay, well, output, if we're talking about the short run, is going to be some function of capital and labor, but what we do is we put a little bar over that to indicate that it's fixed. Okay, it's something that you can't change in the short run. Now, what that means is, if K is fixed, then we can rewrite that production function as just a function now of labor. That means that if you can't change K, then the only thing that matters, the only way that you can change output is by changing labor. Okay? Let's think about that Cobb-Douglas production function, this one, and let's suppose that the amount of capital that we've got is 4 units. Okay, so let's suppose that capital is equal to 4. And there's nothing, I'm going to put the bar over it to indicate that we can't change that. Maybe that's a manufacturing machines that we've got, 4 machines, and we can't get a 5th machine instantaneously. Maybe we could order it, and it could be manufactured and delivered to us in 6 months. But for right now, we're stuck with the 4 machines. And I chose 4 because I can take the square root of that easily. Right? There are some obvious choices for it. If I don't want to get a calculator out, I could choose 1 machine or 4 machines or 16. I could do that. But let's go with 4. What that means is I can plug in that 4. So my Cobb-Douglas production function is 4 to the 1/2 power times L to the 1/2 power. And I can do that in my head. The square root of 4 is just 2. So my production function becomes 2L to the 1/2 power. And you can see that now my production function is simply a function of L. The only way I can change Q is by changing the amount of labor that I've got. We're stuck with the 4 machines. Let's create a table. What we want to do is explore this relationship between labor and output. And the easiest way to do that is to create a table. I'm going to put up here capital, which is K. We're going to think about a level of capital. We're going to be thinking about 4 machines. We're going to also be thinking about labor, which is L. I'm going to put here output. Obviously, that's Q. And then we're going to define a couple things here in a second. I'm going to go ahead and put my columns here. But I'm going to define something that I call marginal product. And I'm also going to define something that I call average product. And we'll fill those in. I'll give you the definitions here in just a second. So we've got marginal product and average product. Now I'm going to think about levels of labor from 0 up to 5. So we could have 0 workers or 1, 2, 3, 4, 5 workers. Now capital is stuck at 4, right? I've assumed that capital is 4, and I've got 4 units of capital whether I'm using 0 units of labor or 5 units of labor. So this doesn't change. It's a fixed input. A fixed input means that it doesn't change. Okay? And then what we can do is we can use this Cobb-Douglas production function. Actually, we can use this one to just plug in different levels of labor and see how much output we produce. If we plug in a 0 for L, well, the square root of 0 is 0, and that means that if we have 0 labor, we get 0 units of output. If we have 1 unit of labor, then I plug in a 1 here. The square root of 1 is 1, and 1 times 2 is just 2. So I can get 2 units of output. If I have 1 worker, and I've got those 4 machines, then that provides me with 2 units of output. If I have 2 workers, then I plug in a 2 there. I can't do the square root of 2 in my head, but I've already done it. If you multiply it by 2, it's going to be 2.83. Same with 3. I would need a calculator, but it's 3.46. 4 I can do. If I've got 4 units of labor, I plug in 4 there. The square root of 4 is 2, and 2 times 2 is 4, so I can get 4 units of output. If I've got 4 units of capital that I've got to work with and 4 workers, I get 4 units of output. And then the 5th, if I have 5 workers, I can produce a total of 4.47 units of output. So there's what output looks like if I use this Cobb-Douglas production function. It's very easy to just plug in different levels of labor. You could easily do this in a Excel file if you wanted to and think about larger units of labor. It'd be very easy to set that up. Let's think about marginal product. Let me give you a definition of marginal product. So I'm going to say marginal product. I'm going to typically abbreviate marginal product MP, marginal product. Marginal product is just how much total output changes or total product changes. Sometimes we call this total product. A lot of times I just call it output. But marginal product is how much total product changes when you change an input. Okay, so here we would be thinking about the marginal product of labor. So I would put a little subscript there. Marginal product of labor is just, this is how we write the marginal product. It's the change in total product, change in output when we change labor. So that delta, I think I've probably used that before, but if I haven't, that triangle, the delta symbol, stands for change in. So it's change in output when we change labor. Well, so we're going to be thinking about going from 0 units of labor to 1 unit of labor, and we can see that output goes from 0 to 2. So our output changed by 2 units. That means the marginal product of the first worker is 2 units of output. If we go from 1 worker to 2 workers, now our output goes from 2 to 2.83, so the marginal product of the second worker is 0.83. That's how much it changed by. Here's what the rest of them look like. It's 0.63, 0.54, and 0.47. So you're just looking at how much output changes at each step. Average product just tells us what's the output per worker. So average product, which we're going to abbreviate AP, and I'm going to put average product of labor. If we had a situation where capital was also changing, we could think about the marginal product of capital and the marginal product of, or average product of capital. But for right now, we're thinking about average product of labor because we've got labor changing. It's just the amount of output that you produce divided by the number of workers that you're using. We can't divide here. We've got 0 workers. We can't divide by 0, so I'm just going to put a dash there. But here, if we've got 1 worker, we're producing 2 units of output. Well, 2 divided by 1, that would be 2. The average product of the first worker is 2 units of output. Here we've got a total output of 2.83, and we've got 2 workers, so 2.83 divided by 2, that's roughly 1.42. Then we have 1.15. Here, this one's easy. We've got 4 units of output divided by 4 workers. The average product is 1. And then 5.47 divided by 5, that's 0.89. So now we've got an idea of, as we're changing labor, what happens to output, and we can think about at the margin. How much additional output do we get out of each worker? And we can also think on average, how much are we getting out of each worker? Now, let's graph this. I want to graph the relationship between labor and output. And I don't need to be real precise with it, but I'm going to put output on the vertical axis. I'm going to put labor on the horizontal axis. And labor goes up to 5, output basically goes up to 5. So if I just make some marks here at 1, 2, 3, 4, and 5, and also labor up to 5, I can do a real quick sketch of what that production function looks like. Remember, this production function is drawn for 4 units of capital. If I have no labor, I get no output. So there's a point on my production function. If I have 1 unit of labor, I get 2 units of output. So there's a point. If I have 2 units of labor, I get 2.83 units of output. So that's somewhere right in there. 3 units of labor, I have 3.46. So that's somewhere roughly there. And then 4 units of labor, I get 4 units of output. That's somewhere right here. And 5 units of labor, I get 4.47. That's somewhere maybe right there. If I were to connect those with little line segments, I would get what ends up being the production function. So we would call that a production function. You can see it's not linear, right? As we increase the number of workers, at the margin, we're getting less and less output out of each worker. And so we need to talk about that. Why is it that our marginal product is declining as we hire more workers, And we have a name for that. We call that the law of diminishing marginal product. Law of diminishing, I'm going to abbreviate marginal product. So let's talk about where the law of diminishing marginal product comes from. This is one of those things that maybe somebody that's older than you might have tried to teach you a lesson when you were younger by saying something like, we've got too many cooks in the kitchen. So if your mom or your grandma, when you were little, if you were in the kitchen and you're goofing around in there and your grandma said, hey, you need to get out of here, we got too many cooks in the kitchen, what she was trying to illustrate to you was a situation where if you've got a fixed input, in the case of the kitchen, it's the kitchen size and the number of stoves and the number of sinks that's fixed on any given day. And so as you add more and more people to that production process, they start to get in each other's way and they have to share input or they have to share the amount of capital that's available. And so everybody's productivity starts to decline. If you get 10 people in the kitchen or 20 people in the kitchen, your output could decline to nothing. You might have so many cooks in the kitchen, nobody can do anything. And so this law of diminishing marginal product is just a real world fact. It's a characteristic of this world that we live in. There's nothing we can do about it. So that's why the production function is not linear, because we've got a fixed input. Now, let's also look at, if you were to graph or to calculate the slope of this little line segment right here, the rise is 2 and the run is 1. That line segment has a slope of 2. And if you calculate this line, the slope of this little line segment, you would see that it has a slope of 0.83. Because the rise is 0.83 and the run is 1. And this one has a slope of 0.63. And this one has a slope of 0.54. And that little chunk has a slope of 0.47. Because the marginal product is always the slope of the production function. And so as we increase the amount of labor, our marginal product is getting smaller and smaller, meaning that this production function is getting flatter and flatter. If we continued this, it would reach a peak and then it would start to go down, and you can get so many cooks in the kitchen that total output ends up being 0. So if you know anything about calculus, then you may know that a derivative is always the slope of the total curve. So if you had total cost, and you took the derivative of total cost, you would get marginal cost. Well, here we've got total product, and if you were to take the derivative of it, which is the slope, you would get marginal product. If you haven't had a calculus class, just pretend like I didn't say anything there. So that's what's happening. That's the law of diminishing marginal product. What I need to do now is I need to clear this off, and then we'll talk about the role of the manager in how you manage this kind of information. The first job of the manager in managing the production process is going to be to make sure that you produce on the production function. In other words, if I go back and I just draw a quick sketch of a production function where we've got labor here and output here, and let's suppose we're using this much labor, we want to make sure that we're actually getting that much output. Right? You can have a situation where you've got workers that aren't doing what they're supposed to do. We've probably all been in a store where you look over and you see people that are working and they're just sitting there on their phone. And what's happening right then is that person is getting paid, they are a worker, but they are producing absolutely nothing. And if you've got that going on, then what you could have is this number of workers and maybe you're only getting that much output. Well, that's the job of the manager, right? Every time I see that, I think there's a bad manager. This place is not being managed effectively. Because what you want to do is make sure that you're up there on that production function. So that's the first job of the manager in terms of managing production. And the second job is to figure out what's the right amount of labor, or capital, or land if it's an agricultural production process. So you've got two things. You've got to figure out the right amount of labor, but then once you've got that amount of labor, you've got to try to get the most out of your labor. And that, getting the most out of your labor, has to do with something that we call incentive compatibility. And we'll talk about that. A lot of times the incentives for the workers or for the manager even don't match up with what's best for the firm. And so we'll think about that later on. Let's start to think about choosing the right amount of labor. Let's begin there. So how do you figure that out? Well, let's think about the value of labor to the firm. So the value of labor, if you're going to hire a worker, the only reason you would hire the worker is their ability to help produce output. Okay, they're a necessary input into the production process. And so if we think about the value of a unit of labor to the firm, then let's go through kind of a little example. Let's suppose we've got a market where a firm can sell output for $200 per unit. Output sells for $200. So if the firm produces a unit of output, it can sell that output in the market for $200. And let's suppose that a unit of labor costs $100. Suppose a unit of labor costs $100. We could think about that as maybe a day or a certain amount of time. That it doesn't matter. Okay. So output sells for $200. The labor is going to cost you $100 to employ it. So what matters is, well, how much output is that unit of labor going to be able to produce? So let's talk about a basic fundamental fact of decision making, and that is something that if you've had a principles class, this is something you would have heard on maybe the first class period or within the first week. If the person teaching that class knew what they were doing, they taught you this. You may not remember it, but here is a fundamental fact about decision making. A decision maker takes an act, let's say a decision maker takes an action. That's probably the best way to say it in this case. Decision maker takes an action if and only if the marginal benefit of that action is greater than the marginal cost. This is something I say over and over. In fact, it wouldn't surprise me if a previous video in this group of videos that I'm doing, I might have already told you this. I will tell it to you again. A decision maker takes an action if and only if marginal benefit equals marginal cost. Well, if we're thinking about taking this action, should I hire another unit of labor? Well, I should if the marginal benefit of hiring that unit of labor is higher than the marginal cost. The marginal cost is $100. So if that unit of labor can produce more than $100 worth of output, then I should hire them. It passes the test of you take an action if and only if the marginal benefit is greater than the marginal cost. So the amount of additional output that the worker can produce is the marginal product. We just defined that. So the amount of additional output the worker can produce is the marginal product of labor, right? It's when we hire that worker. How much more output do we get? Well, marginal product. So let's suppose that when we hire that worker, they can produce one more unit of output. That's how much our output goes up when we hire this next worker. Well, if they can produce one more unit of output and that unit of output sells for $200, then the value of what they produce is $200, which is greater than the 100. I should do that. I can figure out the value of what they produce by taking the price of the output and multiplying it by the marginal product of labor. This is how much additional output they can produce. If they can produce a half a unit, if output goes up by a half unit, when I hire this new unit of labor, then this would be 1/2. 1/2 of 200 is $100. When I hire that unit of labor, they produce output that's worth in the market $100. Okay? And we call this the value marginal product of labor, VMP, value marginal product. So let's write it more generally. The value marginal product of labor is equal to the price of output, which I'm going to call P, multiplied by the marginal product of labor. It's simply the dollar value of the change in output that we get when we hire one more unit of labor. If we were doing it for capital, the value marginal product of capital would be the price of output multiplied by the marginal product of capital. So we can think about this decision-making rule for choosing the right amount of labor in terms of either the input labor or the input capital. Let's add value marginal product to that table that we had. I'm going to create a new table that just has part of it. I'm going to have labor, and remember that was 0 up to 5. And I'm going to have our capital, or excuse me, our output, that was 0 to 2.83, 3.46, 4, and 4.47. And we also calculated the marginal product of labor. That was 2, it was 0.83, 0.63, 0.54, and 0.47. And then we could quickly calculate the value marginal product of labor by taking the marginal product here and multiplying it by 200. Doing this calculation. Well, 2 times 200 would be 400. The value marginal product of the first worker is $400. And then here's what the rest of them look like. It's 166, 126, 108, and 94. There's what value marginal product looks like. So let's think about this rule. Should we hire the first unit of labor? Well, the value marginal product is 400. That's the value of what we get out of them. It only costs us 100, so yes, we should hire that unit of labor. That's a good idea. How about the second one? Well, the value marginal product is $166. That's greater than 100. Yes, that's a good decision. Notice that the value marginal product is declining here. But that's not what's important. What's important is the value marginal product, in this case that would be our marginal benefit, greater than our marginal cost of 100. And that's true also for the third worker and the fourth worker. We get down here and we say, oh, should we hire the fifth worker? Well, what are we going to get? Well, the value of what the fifth worker would produce would be $94, and it would cost us 100 to hire them. We don't want to hire them. Given this information, the right number of labor, or the right amount of labor to hire would be 4 units of labor. If the cost of labor were to change, let's suppose the cost of labor went up to $150. Well, then we wouldn't want to hire the fourth worker and we wouldn't want to hire the third worker. We would want to hire the first and second because 400 is greater than 150 and 166 is greater than 150. But we'd never hire the third worker because they produce output worth $126 and it costs $150. So you can see the amount of labor that we would hire depends crucially on the marginal cost of labor, but also the value of what they produce, the value marginal product. If we were to graph this, I worked through that in terms of step by step. If we could think about the units of labor that we hired as being available in continuous amounts, not just integers of 1, 2, 3, 4, 5, but if we could think about hiring 1.5 units of labor or 3.7 units of labor, then what we would see is that the value marginal product declines as you hire more labor. Put dollars up here. And then we could put the wage right here. That's the marginal cost. And we would see that for all of these units of labor up to this point, the value marginal product is greater than the wage. You would want to hire all of these units of labor up to that point, but this would be the optimal amount of labor to hire. You'd never hire any of these units of labor because the marginal cost is greater than the marginal benefit. So this is what it looks like in a table. If we were looking at a situation where we're graphing it, it would look like that. Okay. Turns out that this thing that we have described as the value marginal product of labor, that's actually the demand curve for labor. So if this was a labor economics class and we were talking more about this in more depth, we would define that as the demand curve for labor. The textbook has a discussion in the chapter that we're going through right now on what are referred to as isoquants. And we're going to skip that. It's something that for what we're doing in this particular video, we don't need to worry about. If you are watching this video for something other than a class that I'm teaching, if you're just interested in understanding this kind of stuff, then you can go see information about isoquants I've got some intermediate microeconomics videos, and there I've got a video on production and costs. It's a lot of what we're doing right here. I go into more depth in that video. So if you're interested in isoquants, go to my intermediate micro video. But for what we're doing here, we're going to skip that. Let's talk about cost functions for a little bit. So up to this point, we've been thinking about production. We've talked a little bit about costs of inputs, but not much. We need to think about more on the actual link between inputs and the costs of production. So we're going to let this C of Q be our general form for the cost function. So it represents the cost of producing output. It's a really important part of the profit maximization decision for a firm. Remember that a firm is seeking to maximize profit, and profit is equal to total revenue, which is a function of output, minus total cost, which is also a function of output. So this cost function is half of the profit maximizing decision. So we're going to be thinking about this chunk right here. We talked about the fact just a little bit ago that in the short run, some inputs are fixed. Capital is fixed, for example, in the short run. Other inputs are variable. And so we're going to be thinking about fixed inputs. A fixed input does not depend on output. Does not, I'm going to underline that, does not depend on Q, output. In that first table we did, we had capital here, it was 4. In other words, it didn't depend on output. We could produce more output, but we were using the same amount of capital. That was our fixed input. We can think about what we're going to call a fixed cost. So because some inputs are fixed, That means some costs are fixed. Whatever the cost of those inputs are, that's going to be what we would describe as a fixed cost. So a fixed cost does not depend on output. So in our next tables, we're going to be thinking about costs, and we're going to see that some of them are fixed, even at different levels of output. Those are going to be our fixed costs. We can also have variable inputs. In this case, our labor was our variable input, and it does depend on output. And because it depends on output, the cost of that labor is going to be a variable cost. Okay, and a variable cost does depend on output. It's also the case, so we're going to abbreviate or fixed costs, we're going to call FC, and variable costs, we're going to abbreviate VC, fixed costs and variable costs. And we're also going to be interested in something that we're going to call total cost, right? And total cost, as you can probably already guess, is going to be fixed cost plus variable cost. Now, what I need to do is I need to link this information up with the total cost curve. And so I'm going to clear this off, and then we'll come back and create another table similar to this one, but with different numbers. All right, let's think about another production process where we have some labor, and we'll think again about labor going from 0 up to 5. I'm going to go ahead and give you output. And let's suppose that we're going to put this on a per hour basis. So just for the sake of the story that I'm going to tell as I go through this example, we'll think about this as being per hour. That's really not that important. We could think about it per day or per month. But let's think about output. If we have 0 units of labor, we get 0 units of output. Let's suppose if we have 1 worker, we get 50 units of output. 2 workers, we get 90. 3, we get 120. 4, we get 140. And 5, we get 150 units of output. And then I'm going to start adding some costs of production. Okay? So let's start by thinking about what I'm going to call the cost of the factory. And you can think about this like it would be the per hour rent that we have to pay on a building that we use. And let's suppose that it's $30. Now, our rent doesn't depend on how much output we're producing. So this is going to be our fixed input. It's the lease that we've signed, and that fixed input generates this fixed cost of $30 per hour, and it's $30 regardless of the amount of output that we're producing. So that whole column there is just 30. We can produce 0 units of output, we still have to pay our per hour rent, or we could be producing 150 units of output and we still are on the hook for that $30 rent. That is what I would describe as our fixed cost. And I'm going to keep it nice and simple in this example. Let's pretend like that's our only fixed cost. And then let's suppose that we think about our cost of workers. Cost of workers, and I'm going to make an assumption here. Let's suppose that the wage is equal to $20. So I'll put up here wage equals $20. So we've got everything per hour. And so that is convenient. If we have 0 units of labor, then we have 0 cost of workers. So that would be 0. If we have 1 worker for 1 hour, then it costs us $20. And if we have 2 workers for an hour, then it costs us $40. You can see that this simply goes up by 20 each time, up to 100. That's our variable cost. Right? It's variable because it depends on output. We need more units of labor to produce more output. Okay? So now let's think about our total cost. So I'm just going to call it total cost. And it is just fixed cost plus variable cost. So if we're producing no units of output, our total cost is $30. We don't have any worker cost, but we still got that rent that's got to be paid. If we're producing 50 units of output, our total cost of production is $50. If we're producing 90 units of output, our total cost of production is $70. You can see that this is going up by $20 each time. So that's easy to fill in. 90, $100, 110. Let's do that. 110, and then 130. So there's our total cost column. Let's graph that total cost curve. So if I were to graph it, I don't need to be real precise. I'm going to put total cost up here. I'm going to put quantity down here. And our quantity is going up to 150. So I'm going to put a 50, 100, and 150. And our total cost is going up to 130. So I'm going to put also 50, 100, and 150. If I'm producing 0 units of output, it still costs me $30. So there's a point on my total cost curve. If I produce 50 units of output, it costs me $50. So there's a point. If I produce 90 units of output, it costs me $70. So 90 units of output, that's somewhere right here, and 70 would be about like that. If I produce 120 units of output, it costs me 90. So 120 would be right about there, and 90 would be somewhere in there. 140 units of output, that'd be out here, and it costs me 110. That's somewhere up here maybe. And then 150 and 130, that's somewhere right up in here. If I connect those, I'm getting what I would call the total cost curve. You can see it's not linear. That thing's getting steeper and steeper. And we'll talk about that. Actually, let's talk about that now, because that happens for the exact same reason that our production function got flatter and flatter, and it was the law of diminishing marginal product. The problem here is that as we want to increase output, we have to hire more workers, but remember, we've got a fixed amount of capital. And so as we bring more workers in, they have to share capital, they start to get in each other's way, and productivity goes down. Which means as we move in this direction, our productivity is going down, but each of those workers is still costing us $20 an hour. And so what we're getting out of each worker is decreasing, but we're not getting a break on the cost, which means our total cost is increasing at an increasing rate. So there's our total cost of production. What I want to do is we need to talk about marginal cost, and we can do it in this table. In fact, I'm going to show you how to do it in this table, but I want to create another table where I've got quantity changing by 1 unit at a time. Marginal cost is easiest to understand if you start by changing output by 1 unit. Here, this table was originally designed to focus on the effect of changing the amount of labor by 1 unit. And as we changed labor, our output was jumping by more than 1 unit. What we need to do now is we're kind of done talking about labor for a second. We need to talk about the relationship between output and total cost. I want to focus on changing output, so I want this column now to change by 1 unit at a time. So I'm going to put another table over here where we have output, and I'm going to start it at 0, and I'm going to go up to 10. And that's going to allow us to focus on small changes, 1 unit changes in output. Let's suppose that our total cost, I'm going to go ahead and give you the last column first in this particular table. This is going to be a different set of numbers than that. So let's suppose our total cost looks like this. If we produce 0 units of output, our total cost is $3. And then I'll just read off the rest of these. Then we have $3.30, $3.80, $4.50, $5.40, $6.50, $7.80, $9.30, $11, $12.90, and $15. This would be a good time to remind you that, in my opinion, the best way to learn from this is if you're doing this with me, right? I'm not writing these down here just to take up extra time. It helps if you're taking notes along with me to be, for me to read these off so that you can write them down as well. You will learn this way better if you write this down. Some of the stuff I go through a little bit quick and you might have to pause it. But if you're just sitting there passively watching this, okay, well, I would say you can learn a little bit from that, but not as much as if you actively do it. So now let's think about what our fixed cost is. And you might think, well, what we did over here is we started with fixed cost and then we did variable cost and we got total cost. How can we do that backwards? Well, notice that if we're producing 0 units of output, we don't need any labor and our variable cost is going to be 0. So remember that total cost is equal to fixed cost plus variable cost. If variable cost is 0, then that means total cost is equal to fixed cost. Okay, well, output is equal to 0 here. That means our variable cost would be equal to 0, which means our fixed cost and our total cost are equal, which means our fixed cost is $3. And because it's a fixed cost, it's $3 at every unit of output. So I can just say, okay, well, it's going to be $3 there. Here, I'll quote all the way down. It's $3. At every level of output, our fixed cost is $3. And then once you've got fixed cost, it's easy to get variable cost because you can just, the sum of this number and this number is going to be that one. So if you take this number and subtract off 3 each time, that tells you what your variable cost is. Here we know that since output is 0, our variable cost is 0. Here our total cost is $3.30. And $3 of that is our fixed cost, which means our variable cost has to be 30 cents. And then I'm just going to read off the rest of these. It's easy here. We could do this one. $3.80 minus 3 is 80 cents. And then here's what the rest look like. $1.50, $2.40, $3.50, $4.80, $6.30, $8, $9.90, and $12. And you can verify that at each step, the $12 plus the 3 equals the 15. $6.30 plus $3 equals $9.30. Okay? So there's our variable cost. Now, let's just briefly, let's graph that total cost curve just so that you trust me that it's very similar to this one. Our total or quantity starts at 0 and goes up to 10. I'm going to put 10 there. And at a quantity of 0, our total cost is $3. So it's down here, $3. And by the time output gets to 10, our total cost is up here at $15. So it's somewhere up here. Let's say 15. And notice what it's doing. It's going up by a little bit, and then it starts to go up by more and more and more. Here it goes up by 30 cents, right? And then it goes up by 50 cents. And then by the time it's going up here it's going up by more than $1 each time. So here's what your total cost curve looks like. Looks very similar to that total cost curve. Let's define some other cost measures. We're going to define what we call, actually I'm going to go ahead and put my columns out here so I don't start writing stuff where I need to put my table. We're going to calculate average fixed cost. We're going to calculate average variable cost. We're going to calculate average total cost. And then we're going to calculate marginal cost. So let's define each one of these. So the first one is, let's start with average fixed cost. Average fixed cost is calculated as just fixed cost divided by Q. Each of these average measures are going to be divided by Q. So average fixed cost, we would take our fixed cost and divide by Q. Now we can't divide by 0, so I'm not going to calculate it right there. But what we're going to be doing here is we've got fixed cost of $3 divided by an output of 1. That means that our average fixed cost is $3. And then we've got $3 divided by 2, that's $1.50. And then $3 divided by 3, that's $1. So you can see that the average fixed cost is easy to calculate. I'm just going to write the rest of them. It would be 75 cents, 60 cents, 50 cents, 43, 38, 33, and 30. There's what average fixed cost looks like. Let's do average variable cost. Average variable cost, you can probably guess, is equal to variable cost divided by Q. If you take your variable cost and you spread it out over the units you're producing, what's your variable cost per unit? That's what this tells us. Same thing, we can't divide by 0 here where quantity equals 0, so we're going to put a dash there. Our variable cost is 30 cents when we produce 1 unit of output. So 30 cents divided by 1, that's 30 cents. And then here our variable cost is 80 cents divided by 2 units of output. That's 40 cents each. Then $1.50 divided by 3, that's 50 cents each. You can see that our average variable cost is simply going up by a dime each time. So that one's easy. Up to $1.20. So there's our average variable cost. And then let's do our average total cost. So average total cost is just equal to total cost divided by Q. There's actually another way you can figure out average total cost. Let's rewrite this. Total cost is equal to fixed cost plus variable cost. Well, if you just divide everything by Q, you get average total cost is equal to average fixed cost plus average variable cost. So we could take our average fixed cost and add to it our average variable cost. So if we did that, we can't divide by 0, so I'm putting a dash there. $3 plus 30 cents would be $3.30. And that would also be what you would get if you took total cost of $3.30 and divided by quantity of 1. Here, it's $1.50 plus 40 cents. That's $1.90, which is what you would get if you divided $3.80 by 2. So let me read off the rest of those. Then we have $1.50, $1.35, $1.30, $1.30 again, $1.33, $1.38, $1.43, and $1.50. There's what average total cost looks like. And then finally, let's think about marginal cost. This is the most important one for this chapter. So marginal cost anytime you've got marginal anything, it's the change in whatever this word is. Marginal, that phrase just means change in. So marginal cost is the change in total cost when you change output by 1 unit. So I'm going to think about defining it as marginal cost is equal to the change in total cost when you change output. Okay. So we need to start with output of 0 and go to 1. So we're looking at how much total cost changes. So from here, it starts at 3 and goes to 330. So it changes by 30 cents. And then it goes from 330 to 380. That's a change of 50 cents. And then it goes from 380 to 450. That's a change of 70 cents. So this is going up by 20 cents each time. Up to $2.10. There's what marginal cost looks like. And you can see that law of diminishing marginal product here. This marginal cost, remember, is going to be the slope of the total cost curve. And as we increase output, marginal cost is rising. In other words, that slope is getting bigger and bigger and bigger. And so our marginal cost is rising because of the law of diminishing marginal product. Okay. What I want to do now is just quickly graph these. I'm going to graph it right in here. And we do not need to be precise with this. I just want to sketch out a graph of what some of these columns look like. Actually, I'm going to focus on the average fixed cost, average variable cost, average total cost, and marginal cost. I'm going to put my costs up here on the vertical axis. I've got dollars, and then down here, that little Q conveniently placed right there is my label for my horizontal axis. And these numbers right here, the highest one of them is 330. So I'm going to have $1, $2, $3, and then my outputs go up to 10. So I'm going to put 10 there. And so all I'm really going to do is just quickly sketch out what this looks like. Let's start with average fixed cost. At a quantity of 1, it starts out at $3. So it starts out right up here, and it ends up at 30 cents. It ends up somewhere right down here. And notice, at first it falls really fast, and then it starts to slow down. So this average fixed cost looks something like this. There's average fixed cost. You could easily do this in Excel and then have it graph these if you wanted, and that'd be very easy to set up. Let's do average variable cost. So at a quantity of 1, average variable cost starts out at 30 cents. That's down here somewhere. And then it's linear. It goes up by a dime each time. It ends up at $1.20 over here at a quantity of 10. So it ends up somewhere right up in here, and it's linear. It simply looks like that, average variable cost. And then average total cost starts out at $3.30. It starts out somewhere up here. It ends up at $1.50, so that it ends up somewhere right in here. And notice what it does. It goes down to $1.30, and then it starts to go back up slowly. So somewhere right here in the middle, it reaches a bottom at $1.30, somewhere right in here. So I'm going to sketch it out. It looks something like that. There's average total cost. Shouldn't have done that. Let's do marginal cost. So marginal cost starts out at 30 cents right here, and it ends up at $2.10. It ends up somewhere right up in here, and it's also linear. In fact, it's got a slope of 20 cents. It's twice as steep as that average variable cost curve, and it actually comes up right through the bottom of that curve right there. So it comes up like that. There's marginal cost. there's a rough sketch of what those cost curves look like. And we're going to be using some cost curves later on in the class, and so the only reason we're doing this is just to get a rough idea of why the cost curves look like this. The important parts are this. Marginal cost is rising. It's rising because of the law of diminishing marginal product. Another really important part about cost curves is this U-shaped average total cost curve. Average total cost goes down, reaches a minimum, and then starts to go back up. That's an important characteristic. In fact, those are the two most important characteristics about this picture. So what I want to do is erase this, clear this off, and then we'll come back and I'll draw a picture of some typical cost curves. All right, let's think about a cost curve picture that we're going to use frequently later on in the class, and that's going to be this picture. So we've got costs up here, vertical axis. We've got quantity down here. We're going to have our upward sloping marginal cost curve. A lot of times I will not draw it linear. In fact, the marginal cost curve can actually, right here, it typically looks like that. It's got kind of a hook on it. I never draw that, and the reason I don't is because that portion of the marginal cost curve isn't useful for anything that we're going to be doing, and we'll talk about that a little bit later on. So when I draw it, I'll leave that portion of it off and just kind of draw it as a little curve, upward sloping curve, because that's the only relevant portion of the marginal cost curve. And then we're going to have our average total cost. It's U-shaped. And the bottom of that average total cost curve, that's where the marginal cost curve intersects it. That's a mathematical fact. If you're not sure why that's the case, then you can go to one of my principles videos on production and costs, and I have a section on exactly why that has to be true, but it is true. And then we've got a average variable cost curve. In my other picture that I just erased, it was linear and upward sloping. Usually it's U-shaped. It's shaped a lot like the average total cost curve. And so I'm going to draw it like this. There's average variable cost. The bottom of that average variable cost curve also is the place where the marginal cost curve intersects it. So that is the typical cost curve picture that we're going to be thinking about. Let's talk about, I mentioned this just a little bit ago, let's talk about how you would calculate marginal cost if your quantity was changing by more than 1 unit. You may see a problem where your marginal cost is changing, but your quantity is changing by more than 1 unit. So let's just run through something where I show you how to do that. Let's go back to that previous table. That previous table looked like this. I had quantity at 0, 50, 90, 120, 140, and 150. And then our total cost, that last column in that table, looked like this: 30, 50, 70, 90, 110, and 130. So there's our total cost if you had to calculate marginal cost. And we're going to think about starting from 0 and going to our next one. So we're not going to calculate it, the first one. Marginal cost is always about going from one place to the next. Well, then you would just use this formula. Marginal cost is equal to the change in total cost divided by the change in quantity. So you'd look at how much your total cost changed. Let's do it from here to here. So from here to here, our total cost changes by 20, but then we've got to divide by how much our quantity changed. Our quantity changed by 50, right? So that would be equal to 0.4. There's the marginal cost of going from here to here. 0 to 50 units of output, our total cost changes by 20. let's think about here. If we go from 50 to 90, well, our total cost is changing by 20, and our quantity has changed by 40. That's equal to 0.5. 20 divided by 40 is 0.5. Then our total cost changes by 20, and our quantity changes by 30. That's 2/3. That's 0.66666. I'm going to say 0.667. And then our total cost changes by 20, and our quantity changes by 20. That's $1. And then our total cost changes by 20, and our quantity changes by 10. That's equal to 2. So there's what marginal cost looks like in that table. And you can see marginal cost is rising. I think it's easier to think about the idea behind a marginal cost if you start by thinking about a table where your quantity is only going up by 1 unit at a time, but it doesn't have to. Let's talk for just a little bit about sunk costs. So a cost is sunk if it's already been committed and cannot be recovered. So a sunk cost is very different than what we would talk about as an opportunity cost. An opportunity cost depends on, the magnitude of the opportunity cost depends on the behavior that you take. An opportunity cost is something you have control over. Okay? It depends on what you do. A sunk cost doesn't. A sunk cost is a cost that has to do with a decision that was made in the past, and now you have to bear some costs that you have no control over. What that means is, because a sunk cost is something that is lost forever, it's irrelevant for making decisions from this point on. In other words, there's nothing you can do about it. So let me give you an example. This is something called the sunk cost fallacy. The sunk cost fallacy, the idea behind that is that there are lots of times when we make a decision, and part of our decision-making process involves a cost that we have no control over. And if you do that, if you let that work its way into your decision-making process, and it is part of what determines the decision you make, you've fallen victim to the sunk cost fallacy. Let me give you an example. So let's suppose you own a business, and your business runs events, and let's suppose you lease a building downtown Kansas City, and that costs you, you lease it for a month, it costs you $5,000 rent. So that's a lease payment for 1 month. There's nothing you can do. You've signed the paperwork. You are now on the hook for that $5,000, and you can't get it back. And then all of a sudden, your event falls through. The event is canceled. You cannot get that lease money back, and now you've got to decide what to do moving forward. Let's suppose you have the opportunity to sublet it for $2,000. You can sublet for $2,000. Well, if you sublet it for $2,000, you lose $3,000. If you sublet, you lose $3,000. Right? You're going to pay $5,000. You can sublet it for $2,000, but at the end of the day, you've lost $3,000. However, if you don't sublet it, you lose $5,000. If you don't sublet, you lose $5,000. What should you do? You should sublet it and lose $3,000. Losing a smaller amount is better than losing a bigger amount. Here's the point. The magnitude of this doesn't matter at that point, right? In fact, these numbers don't really even matter at that point. The decision of whether or not you should sublet it or not sublet it should have nothing to do with that $5,000 payment. You're on the hook for that, whether you sublet it or whether you don't sublet it. You should ignore that. From the point of view of making a good decision right now, all that matters is this piece of information right there. I can get $2,000 if I sublet it, or I can choose not to sublet it and not get anything. Getting the $2,000 at least helps me cover part of that money that I have lost. If I choose not to sublet it, I just lose the full $5,000. It's something that seems obvious when you look at an example like this, but it's also one of those things that you're going to catch yourself for the rest of your life occasionally letting a sunk cost sneak in there and invade its way into your good decision making. It's what people mean when they say don't cry over spilt milk. If you're crying over spilt milk, that means that you're devoting your effort and your thoughts to something that you can't change. Let's think about, and this will come back a little bit later. You may say, well, why are we worried about this right now? Well, sunk costs are part of this picture. Your fixed costs are sunk. Okay? And so we'll come back to that a little bit later. Let's talk about algebraic forms of cost functions. So I wrote a cost function just in general as C as a function of Q. And sometimes I will tell you that I accidentally will write this, total cost, as a function of Q. They're the same thing. I teach lots of different classes, and in some classes the textbooks use this, and in other classes the textbooks use that, and so I use them almost interchangeably. If you see something and you're just not sure, contact me and I'll tell you what it means. So let's think about what those might look like. If I were to say, okay, well, let's talk about what I'm going to call a cubic form of a cost function, then a cubic form of a cost function would look like this. It would be equal to F plus A times Q plus B times Q squared plus C times Q cubed. That's a cubic function, meaning that the highest power in that function is a Q that has a power of 3. It's cubed. This we have called F because that would be our fixed cost. It doesn't depend on Q. So this would be fixed cost, and this chunk out here would be the variable cost part because it depends on Q. All of the terms that have a Q, well, that stuff would all be the variable cost, and that chunk right there that doesn't have Q, that would be the fixed cost. If you've got a cubic cost function, then your marginal cost function, which is also going to be a function of Q, that will take the form A plus 2BQ plus 3Q squared. That should have a C. 3 times C. There should be a C right in there. 3CQ squared. If you've had any calculus and you know how to take a derivative, then this makes perfect sense to you. If you take the derivative of this function with respect to Q, you get that. If you don't have any background in calculus, that's fine. This, if you were to see a cubic cost function, you could easily write the marginal cost function that goes with it. Let me give you an example. Let's suppose I said that, let me give you an example of a cubic cost function. 100 plus 5Q minus 2Q squared plus 4Q cubed. There's a cubic cost function where we've replaced the F and the A, B, and C with some numbers. Well, our marginal cost would be, if you take the derivative of that, you get 5 minus 4Q plus 12Q squared. And you can verify that I've just used, actually I didn't, I know how to take a derivative, but if I didn't, you can verify that this matches up with that. So there's a cubic cost function. We could also use a quadratic cost function. Let's put a line here. If we had a quadratic, so there's cubic, quadratic, cost function would look like this. The highest power would be 2. It would be F plus A times Q plus B Q squared. Here's the fixed cost. These are the variable cost. The marginal cost that would go with that would be A plus 2B times Q. Let's do a quick example of that. If I gave you an example of a quadratic cost function of, let's say, 20 plus 6Q plus 3Q squared, then the marginal cost curve would be equal to 6 plus 6Q. So you can see that these look complicated, but they're actually not. If you wanted to understand the cost of producing, say, 7 units of output, you'd say, okay, well, if I wanted the cost of 7 units of output, I just, everywhere there's a Q, I'd put a 7. So it'd be 20 plus 6 times 7 plus 3 times 7 squared. And that would tell you how much output you could produce with 7 units, or the total cost of producing 7 units of output. And if you wanted your marginal cost, you'd just plug in 7 right there, and it'd tell you the marginal cost of the 7th unit. So cost curves are easy to work with. Let's talk about costs in the short run and the long run. So we've been thinking about the short run where you've got a fixed cost. And so you know that all of this is short run because we've got fixed cost here, fixed cost. If we were to now move and think about the long run is the situation you're in if you can change everything, right? You're not stuck with a certain number of machinery. Like you don't have just 4 machines. If we were thinking about the long run, we could say, okay, well, let's just think about producing with 2 machines, or we could have 6 machines, or we could have 60 machines if we wanted. So let's think about that. The key here is that in the long run, all inputs are variable. In the long run, all inputs are variable. Let's suppose that we were thinking about producing output. I'm going to put output on my horizontal axis here, and I'm going to put costs of production up here on my vertical output, or my vertical axis, cost of production. And I'm going to stretch this horizontal axis out a little bit more. We could think, let's suppose before we've ever built any plant, let's suppose we said, okay, let's start by thinking about the size of plant we want. Well, if we build a plant, then we could think about the average total cost curve that goes with that particular plant. It's going to be U-shaped. I'm going to draw a U-shaped average total cost curve that goes with what I would call a small plant. So I'm going to say small. I'm just going to put an S there. That would be the average total cost curve that goes for a small plant. We can produce small levels of output with that plant. And then let's suppose that we thought about an average total cost curve for a medium plant. I'm going to draw it down there. This would be an average total cost for a medium plant. Or we could think about an average total cost curve for a large plant. Let's say average total cost large. Those are just 3 of an infinite number of plant sizes that we could produce. In fact, there are plant sizes in between small and medium, and in between medium and large. And if I were to draw all of the possible plant sizes, the average total cost curves that go with them, this would just start to look like a big bowl-shaped area. And then if I just drew a little line along the bottom of that bowl-shaped area, that line would be what we call the long-run average total cost curve. Now, if we want to focus on the long-run average total cost curve, I'm going to get away from this picture and just draw a long-run average total cost curve that looks like that. Long-run average total cost. Here's quantity. Here's costs. So now I've just got, and I've kind of put a long horizontal segment on there. Let's talk about how you would use this long-run average total cost curve. Let's suppose that we built a plant size. Well, if we build a plant size, there's our short-run average total cost curve. I'm going to call it short-run average total cost curve. We've built that particular plant size. Let's suppose we're producing this level of output. We'll call it Q1. And we decide that we want to produce more output. Let's suppose we want to produce Q2. Well, here's what this picture tells us. This picture tells us that if we produce Q2 and we continue to use the same plant size, our costs on average are going to rise to right there. But what this long-run average total cost curve tells us is that we could reduce our costs on average to right there, but not with that plant size. We would need to build a bigger plant. So if we built the plant size that's the right plant size for producing Q2, it would be that plant size that corresponds with that average total cost curve. Notice that makes sense to a lot of people when you think about increasing output. It makes sense to fewer people when you think about decreasing output, but it's the same thing. If we decrease output and we continue to use the same plant, our costs go up on average. If we built a smaller plant, we would be able to reduce our costs on average. The key here is that you want the right plant size in the long run for the amount of output that you're producing. Let's talk for just a second about, draw one last long-run average total cost curve, and I'm going to put some areas on here. So this is a long-run average total cost curve. Here's quantity, here's costs, and let's think about, notice that as we increase output, we're always going to be thinking about moving in this right direction. As we increase output, over this range, costs on average are decreasing. We say that the firm is experiencing economies of scale. So this is economies of scale. I'm just going to write economies. Let's talk about what causes economies of scale. Economies of scale are caused by the fact that as you increase the production process, your workers can specialize in tasks. If a worker is specializing, they don't have to waste time setting one set of tools aside and getting another set of tools. They can specialize on a particular task and get really efficient, and that efficiency drives costs down. So economies of scale are caused by efficiencies of getting bigger. Over here, as we increase output, our costs are going up. We call that diseconomies. So what causes diseconomies of scale? Well, when you get really big, really large production processes are hard to manage. You need lots of levels of management to manage them. And the problem with adding layers of management is that your costs are going up more proportionally than the output that you're getting out of them. And it drives your price or your costs of production up. And then this middle part, notice that your costs on average aren't doing anything. As we increase output, they're just staying constant. We just call that constant returns to scale. It's not caused by anything. It's just the lack of economies of scale and the lack of diseconomies of scale. In terms of, you might wonder, well, how do we get a cost function? If you're running a business out there in the real world, how do you get a cost curve like this? How would we know what A is for our business? How would we know what B and C are? That's where regression analysis comes in. And in another section, we talk about regression analysis, but if you were to look at the relationship between the amount of costs that you incur and the amount of output that you produce, you could use regression techniques to estimate this. It's not very hard. So that's where you would get the information for this. There's one last section in the chapter on multiple output cost functions. We're not going to worry about that. Same thing as before. If you did want to know about that, you could go to my intermediate micro videos and you could find that information there. But for what we're doing here, it's not important. So I'll see you in the next video.